maybe it's just me. Stay. Come on back in. Maybe the effect was just on me. All right. Well, hey everybody, how you doing? Welcome back to Physics with Dr. T. And today we've got Math Bar joining us. We're going to do some brand new physics that for the semester, which is looking at the wave nature of light. Light turns out to have both wave and particle characteristics, and for the next couple of weeks we're going to explore the wave nature of light. We're going to start out with characteristics of light that we can use to test this, which is referred to as diffraction. And this diffraction uses interference. And so in order to talk about these concepts, I'm going to turn this over to Math Bar, and he's going to talk a little bit about the theory that we're going to be exploring.
Okay guys, so this guy, we can try to figure out the wave nature of light by using this demonstration. So once the plane wave move on, during the course of that plane wave, if we choose a point, then this point can act as a point source. So you can see in this figure the point source act as the source of the waves. So from every point source, the wave goes outwards, making a spherical wave front. So this type of point source, during the course of time, they move with the same velocity of the wave front, and they will create a wave front. And this is the way the wavelets, the wave front move. So practically, or you can say that experimentally, when the wave front will strike when the very small hole or the sharp edge, that will also act as the point source, and the spherical wave front will create from them. So if two or more than two of this kind of spherical wave front will combine with each other, then an interesting optical phenomenon happens, and that is the interference. You can see over here. So if we assume two wavefront A and B with similar amplitude A, when they will combine, when they are in the phase, the constructive interference takes place, and their amplitude will sum up and becomes twice A. In this similar way, if the two wavefronts are in out of phase with the same amplitude, they will sum up to give the zero amplitude. It doesn't mean that the light has gone away, rather the light has a zero amplitude over that space.
So now, before we get into the actual experiment, let's talk about this week's PreLab activity. For the first part of your PreLab, please navigate to D2L and follow the link for Waves on a String, and watch the short video there that covers the lab that you haven't done and will be set up in the lab for your review, but you do not have to do. Please watch at the very least the most important segment, which is the equipment segment, from 3 minutes and 7 seconds to 5 minutes and 52 seconds. So for the second part of your PreLab, what you need is just a simple geometric shaped dish, pan, tray, even a sink, what have you. And just a little bit of water. You don't need too much. If you have too much water in there, actually it will other effects will start to overplay, and we just are looking for some simple evidence of geometric reflection of waves off the surface and that there's interference. So I've got this object here. I'm just going to use a can. I'm going to bounce it into the water at a regular pace. And what you're looking for is this area right here. You're starting to see some sign of that. And if you can get a photo of that and include that, that will do the trick for your PreLab. And you'll have demonstrated interference, wave interference in water. You'll have seen it in the simulator, and that should refresh your idea about wave interference ahead of the diffraction lab. We'll see you guys in the lab. In order to do the PreLab today, you'll want to go to the link that's provided in the PreLab guide. This is the wave interference lab, so you just want to go and click on the wave interference, double click on that, it'll bring up this page. Now, the entire point of this is simply to demonstrate interference with water waves. So this simulates water waves
And that way you can look for that. Now, this simulator is limited. It doesn't have walls for the water waves to bounce off of like you would see in a swimming pool or some other container. And so what you want to do is you come over to the side, over here to the uh, control panels, and we're going to move the frequency to the maximum. We're going to get the best kind of quality, and the amplitude needs to be max so that you have the nice, clearest, crisp waves to operate with. The separation of the two hoses, or the two faucets in this case, should be max. So you just bring that all the way out to 5 centimeters. And again, we want this to be water waves. You can explore sound waves, and you can explore the laser beam, and I encourage you to do that on your own. But for the pre-lab activity purposes, you only simply need to click on the water. Now, when you click on the water droplet, it will begin dripping water into this simulated water surface, and you see ripples are formed. But as I said, there are not any reflected waves, and so there's no interference pattern. However, it is the characteristic of waves when they bounce off of a surface, as you may recall from the waves on a string experiment, that those waves will reflect back in an identical fashion. So if we use the second water source and start that as with a drip, it will behave as the halfway point between those two will behave as a surface wall. And you can see a diffraction pattern now begins to appear. So all you need to do at this point is once you've produced this wave pattern, you click pause. You'll do a screen capture of this, and then you'll go to the next step and look for this wave pattern in water.
In order to perform your experiment, you will need the wooden setup, but you also need a diffraction grating. A diffraction grating is basically a piece of plastic that has had lines carved into it in such a way that when light passes through it, behaves as though it's passing through an actual slit in a solid surface. And if you can tilt this sideways, you can maybe see how it affects the light coming through it from the target that I've got on the board here. You also are given a laser pointer. Again, it's just make sure that points down, make sure it makes a nice solid bright light. If you don't think the light is bright enough for your experiment, just let me know and we'll get new batteries. Your source is basically, it's got a groove for your laser pointer to set in. It also has grooves for your diffraction grating to sit in as well. Once you have those set up, you can just slide this back and forth gently in there, twist it as you need to if there's any funky effects that should be recorded but don't need to be part of the actual experiment. You'll notice that this line is measured a certain way, so you'll measure from the front edge of this to the front edge of this board where your paper is going to be set. The challenge that you'll have is to make sure that your measuring stick is actually reaching that point. It can be a little bit awkward to try and get to measure this and still measure everything accurately. There is a groove in here that is designed so that this is effectively flush with the surface of the board. There is some uncertainty in there, and so you may come across some unexpected errors in your experimental setup when you do that. But the idea is to slide this into the groove here so that you can get the most accurate measurement of your distance to the source for your image projection. Okay, great. So now that you've done the pre-lab and you've reviewed the theory, now it's time to go ahead and get into the experimental setup. And the experimental setup for this lab is actually fairly straightforward. It's actually a couple pieces of wood, some diffraction gratings, which we'll look at, and a laser pointer. We have this large expansive wood. Its job is to block the light from burning anybody's retinas out, but also its job is to hold up a sheet of paper that you will tape to it in the right position and make your marks upon so that you can make measurements more efficiently. In order to do this experiment, you want to have your laser beam passing through the diffraction grating that you have mounted on this support, and that beam is going to spread out and project its interference pattern onto the paper. And your job is to make sure that this is done to the most efficient way. The problem is that you cannot assume that just using one measuring stick is going to get you the right distance. So what you'll need to do is measure with two measuring sticks, and you'll place them down in such a way that you have them both measure the same exact distance from the board. And what you need to do is adjust your setup. Try to avoid the board the least because it's so heavy it can really throw off. It's a lot harder to adjust this with fine motion. You want to adjust the laser beam support, also known as the source. So once you've got those lined up, you make that measurement. In this case, I'm measuring 80 centimeters between the beam edge, which is the diffraction grating. Make sure you measure from the diffraction grating mark, not the edge of the wood, to the wood itself. And then once you put it in place, and you can notice that moving it back and forth, you want to take the time to observe. As you slide this back and forth, does it change anything on the board? And the answer should be no. But once you get that in place, and be careful not to move that, you're ready to go ahead and perform the experiment. You make marks, exactly all the points where all the dots are with a good point. You'll also notice the intensity of the lights. You are ready to take measurements and begin your analysis of the diffraction pattern. Once you turn on the laser, you can see that a diffraction pattern will appear on your board. Your job from there is to mark those points on your piece of paper. Let's go ahead and indicate on your piece of paper when you mark them down the level of intensity. Start with 1 being the brightest one that you observe, and then anything that's less bright than that, mark as a 2, 3, 4, and 5, and so forth, and decreasing in intensity. Once you've taken the data, the only thing next to do is to analyze it and, of course, write a report on it. Yes, I'm afraid that you're going to have to write a report on these ones. But hopefully the examples that have been put up onto D2L for you and your classmates to take a look at may help enrich your ability to improve lab writing skills and to make sure that you're producing the best quality lab report you can. In this case, we have data that you've taken strictly in the lab. There's no Pasco setup, so your job is to organize the data in a logical way and make sure that you present it in your lab report and discuss it. Make sure that you go beyond just this is the data, this is the data. And you can see the examples that I've put onto D2L in the sample lab reports, the poor, the average, and the excellent versions of the sample lab reports. If you have any questions at any time, of course, you can always submit your lab report to your lab TA just to get their opinion, any suggestions that they have to help you write to improve it and put any polish on it. And I think that covers everything for this week. Well, that does it for this week's walkthrough. I'd like to thank once again MathBar for joining us, walking us through a little bit of the theory. Hope everybody have any questions. Make sure that you ask your TA, your learning assistant. You can even ask me. And for now that you're ready to go, and let's all do the wave. See y'all in the lab.
Football, soccer field, looks like wave when the people stand up to cheer out their players.
Hey everybody, how you doing today? I'm Dr. T. I'm joining you, and that's the first outtake of it. And then you perform the analysis. Oh, that would be so funny if you were off to the side and you came in and you did the third one. Would you be willing to do that?
No problem. Like this?
Yeah, like this.
Like this.
So here we go. Okay, so, all right, everybody. Thank you very much for joining us this week's walkthrough. I hope that you find the lab to be fairly straightforward to walk through, and we can go out there and learn a little bit more about the wave. That was terrible, so I'm going to do it again. Once you've got your experimental once you've got your experiment set up in an ideal fashion, you can go and make your measurements, and that's going to be do the wave. See y'all in the lab. Oh, I love it. You guys are great. All right.